What is the neighbor discovery process all about? Well, it's all about figuring out the link address of a device in your local area network. So what is a link address? A MAC address. That's all that is. So in this particular example here, we're referring to figuring out the MAC address of host B. That's all. So what is the MAC address of host B? And then we expect host B to respond with its MAC address. Neighbor discovery is equivalent to ARP, but it works in a completely different way. So let me remind you what ARP is for IPv4. We have ARP, which is a broadcast that goes out to absolutely everybody in the local area network. And then the device that has the IP address that we're looking for the MAC address of, then they will respond with the ARP reply unicasted back. So it's as simple as that for ARP. But it's an inefficient process for IPv6 because it relies on broadcasting. So what are we going to utilize here for this neighbor discovery process? We're going to use multicast. That's right, multicast in order to accomplish this neighbor discovery process. So we have a neighbor solicitation message, and the neighbor solicitation message is the message that goes out. It's multicasted out into the local area network, and it says, hey, what is your MAC address? And then we have a unicast reply that comes back. So let's really understand how the addressing works here. This is really complicated, but it's the way it's designed. So we know the IPv6 address of who we're trying to talk to. We know that. Why? Because we would have either typed it in or we would have used DNS to resolve the address from the host name. Very important concept. And it's the same concept of IPv4. If you know the host name, then DNS gives you the IPv4 address. In this case, if you know the host name, then DNS is going to give you the IPv6 address. Or you type in the addresses yourself. So I know who I want to talk to. But remember, we're not broadcasting out anymore. We're not saying, hey, if you own this IPv6 address, give me your MAC address. That's not how it essentially works in this case. Here's what happens with IPv6. Whenever you have an IPv6 enabled interface on a device, the device joins very specific multicast groups. So one of the first multicast groups that every device joins is the FF01. Let me repeat that. FF02 1 multicast group. Okay, that's what it was. So FF02 1 multicast group. That's what every device joins. Every device. Why? Because that is the all nodes or all devices multicast group. What that means is that if you need to talk to every single device in a local area network, you simply send that piece of information to a destination of FF02 1. Kind of sounds like broadcasting. It is, but it's only going to be used when absolutely necessary. So the goal is to not use it when not needed. So as a result of that, we need very specific multicast groups for all of the different services. So in this case here, when we use the neighbor discovery process, every device joins its own multicast group. That's right. It really does. Every device comes up with its own multicast group. So that way there, if somebody wants to talk to you specifically and nobody else, they can talk to you via that multicast group. That's right. You're going to be the only member of that multicast group. So how do you come up with this address? You take the very lower 24 bits of your IPv6 address and you create what is known as a solicited node multicast address. So this is for you personally. A solicited node multicast address. So you are FF02 FF followed by the lower 24 bits. So this is consistent for every single device. And then just the latter 24 bits are going to be utilized. And you might say, well, is there a possibility that this could be unique? Not in a local area network. The odds of that are so slim. It could be, but so slim. The lower 24 bits of any address, well, if you're using EUI64, they're going to be unique. They're going to be unique. Or else that means we have two MAC addresses that are potentially the same. So those lower 24 bits, the odds of them being the same are so slim. If you're using the random generator for the client for the lower 64 bits, well, the latter 24 bits, again, should be super unique. The odds of two devices in the same local area network having the same lower 24 bits is so slim. Slim. And if we had two devices with the same lower 24 bits, well, it wouldn't really matter in the grand scheme of things, because that means then the two devices would receive any messages destined to that particular group instead of just one. But it still doesn't go to everybody, right? So it's still better than broadcasting, because broadcasting would go to everybody, where potentially anything is sent to this particular group that we're creating right now, well, it would only go to the one or two devices that potentially could be in that group. But more than often, it'll just end up being one. The odds of having two or more is pretty slim when you let the devices just do what they need to do and you don't interfere. So now what happens? Well, we have every single device coming up with their own solicited node multicast address. So now when I'm using the neighbor discovery process, I am sending my neighbor discovery message, which is the neighbor solicitation message, to the solicited node multicast address. That's right. So every device creates their own, and then I will send to them based on this address. And then you might be saying, well, how in the world do I know this address? Right? If every device comes up with their own, how do I know somebody else's address? It's simple. It's simple.